Sarah.
Good morning.
Good morning to you. Good afternoon from Europe. And Iris, you hear me?
Yes, I can hear you.
Yeah, and yeah, Iris, I think I see.
Yes,
Okay.
I can
Yeah.
hear you.
Okay,
Sorry,
good.
I was on mute, so.
No. Yeah, it's okay. So, yeah, let's wait for others. Good morning, May.
Good morning.
It's quite early.
Oh no, it's like
Huh?
7.
Okay.
It's not quite early. It's
Yeah.
just
Okay.
yeah,
Not
it's
that bad.
fine. Yeah. It's not like 4 or
Yeah. I didn't know.
just trying to like wake up. I set my alarm for 6 so that I would be like functional.
Yeah. Okay.
So Sarah has the final version of the slides.
Yeah.
I
Okay.
just sent them.
Yeah. Yeah,
I just hit send.
Okay.
just send it to with copy to all, and Shariful is there, so he will be able to project if there's any problem. Yeah, basically, I would ask all the presenters to project your own slide, but I know that the main ones are quite a consolidation of everybody. So perhaps you're switching from one speaker to another. So perhaps I will trust May to kind of call on speakers and so on.
I think we have it together, hopefully.
Okay. Yeah.
And Seth is not here yet.
No.
Seth is at Storm Peak, so he's
Oh.
actually kind of at a remote location, but they have good, we talked to him last night. They have good internet. So do you think the panelists will want to see us, or should we just not have our video?
Yeah, that's a good question. I think, yeah. Well, let us have the speakers video on and others off, and when
Okay.
we have and it's up to you how you and yeah
Okay.
for your part. Yeah, I think it's better to have a speakers video on, and that this panel discussion, perhaps all of us can switch our video on.
Okay. How many people do you have signed up?
Well, people seems to be quite busy, so I think that in terms of the registration, it's about 25 or something.
Okay.
Check. Yeah, so in our system, it's only 25.
That's too bad, but we'll at least get the message out to some people.
Thanks. That's good. And also, this is YouTube streamed through our YouTube channel. This is Minamata
Yep.
Secretary's YouTube channel. So maybe there are some people watching. Don't have Milena yet. Seth, good morning. Do you hear me? Seth, do you hear me? Your microphone was on, but now I see your microphone is muted. Hi, Milena. Do you hear me?
Hello, do we hear each other? I'm just checking. Melina here.
Yes, I hear you. So I think everybody is okay, but
Isako, everything is okay? I don't hear
do-
anything.
oh, you don't hear me? No. Oh,
No, now I hear you. Yes.
okay, good. And so I think everybody's okay, but I don't think I heard from Seth. Seth, can you try unmuting yourself and speak? We don't hear you. I think there's something wrong in your microphone setting.
How about now? Can you hear me now?
Yes, perfect. Good, very good. So I think all the panelists are here, and it is 4 o'clock here in Geneva. So I think we can start. Good morning, good afternoon, good evening, ladies and gentlemen. We only have very few attendees at present, but since we have 2 dozens of registrants, I think other audience will join soon. But while waiting for others to join, I think we can start. So a warm welcome to this Minamata online session, Mercury Science stream. And while many of the people involved in the Minamata Conventions have been busy in preparation for COP4 later this month, we are very glad that we were able to organize this session in collaboration with the International Conference on Mercury as a Global Pollutant, ICMGP. This series of event, Minamata Online Mercury Science Stream, is a good example of science policy interface, scientific community providing input to policymakers and policy community providing input to the scientific community on policy needs. In this Minamata Online Season 2, we work very closely with the ICMGP, and we decided that to provide the opportunities for the organizers of ICMGP workshops to convene sessions within the Minamata online webinar to connect scientific and policy communities. So before going into the substance, I would like to make a bit of housekeeping announcements. And we are using the WebEx platform, and you can open the participant panel and the chat panel by clicking the respective icon at the bottom right corner of your screen. If you have any questions, you can please type questions in the chat box and send it to everyone. I think it is the best way is to send to everyone rather than directing to the specific speakers. And you can type your questions while you're listening. And at the panel discussion session, we will look at the questions in the chat box, and that will help the panel discussion. If you need any technical assistance, please put your message in the chat box and send it to the host. The host is, I think, indicated as Minamata Sek Shariful Islam host. So please send it to him. And please kindly note that this session is recorded and broadcasted, and the recording of this session and the presentation slides will be made available through the Minamata Convention website after the session. So I would like to provide a bit of introductory remarks about the topic of this webinar, which is about the mercury in air. And the reason why the Minamata Convention exists is that the mercury is a global pollutant owing to its long-range atmospheric transport, persistence, the bioaccumulation, and the environmental health hazard. So the long-distance transport, atmospheric transport, is the key for the mercury being regulated at the global level of its Minamata Convention. And it is clearly stated in the preamble to the Minamata Convention. If you can go to the next slide. So the objective of the Minamata Convention is stated in Article 1, which is to protect the human health and the environment from emissions releases is mercury and mercury compounds, which travels and gets into the environment and the human body, as you see in the picture in this slide. Next slide is about the science and monitoring. And Minamata Convention has Article 19, which is about research, development, and monitoring. And the convention requests the parties to cooperate in the modeling and geographical representative monitoring of levels of mercury and mercury compounds in vulnerable populations and in the environmental media. Also, the Article 22 provides that the conference of the parties will evaluate the effectiveness of the convention based on the comparable monitoring data in the environmental media and also in humans. So the representative data, comparable data are key to the implementation of the Minamata Convention and also the effectiveness evaluation. But here's the question: what is the representative monitoring data? What are the comparable monitoring data? This is for policymakers, it may be a simple question, but if you go into the scientific discussion, there's the challenge, and also the scientific community would have a very need to convey a important message to the policymakers what science can inform the policy community on the monitoring the mercury in air. Next slide, please. So this is a very small slide, but the one of the most important the publication in the mercury in the environment is the Global Mercury Assessment 2018, which is published by the by UNEP, and in this, there are many pieces of information on the geographical pattern of mercury in the environment. But this graph, the graph, the chart on the left is about the mercury concentration along the different latitude, and which comes from the elemental mercury monitoring in various locations, and also the trend, the temporal trend is also evaluated currently using the elementary mercury monitoring data. Next slide, please. So, today's in today's session, we first invite Dr. Lenny Martin, who is the ICMGP chair and also the main author of the guidance, the draft guidance document on air monitoring for the effectiveness evaluation, who will speak to the how the monitoring data can be used for the effectiveness evaluation. And then we will have Iris de Krom of National Metrology Institute of the Netherlands to speak about the elementary mercury monitoring measurement. And then these two presentations will be followed by a joint presentation by May Gustin of the University of Nevada, Reno, and Milena Horvat of Joseph Stefani Institute of Slovenia, Cecil Ryman of University of Utah, and Sarah Durham Cheatham of the University of Nevada, Reno, about the monitoring of reactive mercury, which is the main topic of this session. And then this presentation will be followed by panel discussion moderated by Milena. So with this, I think I will turn to Lin Will, who will first represent the ICMGP and then provide the introductory presentation on the air mercury monitoring. Over to you, Limio.
Thank you, Isaku. I hope that everybody can see my screen and it's in presentation mode.
No, it's not in presentation mode, but we can see it. But yeah, it's
supposed to be now.
It's okay. Yeah, it's now. It's okay now.
Okay. Good. Okay, thanks. So from my side, good evening to the delegates or participants in the East. Afternoon, those that's my latitude, and good morning to those in the West. It's indeed again a privilege to be with you and host this joint seminar or online workshop in collaboration with the Minamata Secretariat. I think this is our first webinar for this year. And I mean, since we started with this event in 2020, and so far this is Minamata season online 2. And the feedback that we've got so far has been very positive. I'm just going to give some latest update in terms of the ICGMP Mercury conference. That is now a virtual conference that will take place from the 24th till the 29th of July. Next slide. Check. Okay, yeah, okay. Next slide finally. So, I mean, most of you that have attended this Minamata online sessions before. So this is the executive committee of the ICGMP 2022. When we decided to have a virtual event, we sort of changed the scope as well as the theme, and we've added a few members. So Sandy, Stefan, and Joseph and Asif joined the executive committee after we've decided that the 2022 event will be a virtual conference. Just some of the latest news is that earlier this year, the Lifetime Achievement Award winner was announced, and it's our privilege to announce that Rob Mason from the USA. He was actually born in South Africa, but he's been living in the USA for about over 30 years. He's the next receiver of the Kathy Mahaffey Lifetime Achievement Award. The previous winner was Melina. That's also part of the discussion here today. So Rob was the winner for this year's LAA as the LAA winner. In terms of the call for papers, that has been out for some time now. The closing date was yesterday, the 28th of February. But as the executive committee, we've decided to extend the deadline for abstracts. So the final deadline for abstracts for ICGMP 2022 will be the 15th of March. So please convey this message to some of your colleagues who were still thinking of submitting an abstract. So the new closing date is the 15th of March. Then in terms of the conference, as you know, the workshop has always been part of the conference. So the week before the conference, we will have the workshops. Currently, there's about 13 workshops that has been confirmed, which will focus on AGM, coding, research in the Arctic, etc., etc. And then there will also be a workshop on reactive mercury measurements, which will also be presented by May Gaston and the team from her university. In terms of the plenary sessions, so we will start on the Monday with a plenary talk that will focus on global change in the biogeochemical mercury cycle. Then on Tuesday will be what we call Health Day Tuesday. So we will start in the morning with the Minamata storyteller that will set the scene. And then later in the afternoon, the plenary that will focus on the correct use of mercury guideline values by non-health experts. On the Wednesday, we've decided to focus more on the younger generation, the up-and-coming researchers. So this plenary will focus on future of mercury research at a glance. And we've identified 3 up-and-coming mercury researchers that will then each give a presentation of about 20 minutes. And then on the Thursday, we will focus more on the industry in terms of the industrial emission and challenges. So that will be the 4 plenaries for the week. And then on the 24th of March, we will have the 5th Scientific Steering Committee. And this is where we will look at the abstract which was submitted, and we will finalize the final program. And then registration, once we've paid attention to that and got everything fixed and ready, then registration will open middle of April. But we will again send out an email notifying people that the registration has opened. So this is from the ICGMP desk, just to give some highlights and just some feedback. So my role, I'm wearing 2 hats today as the ICGMP conference chair, so I'm done with that part. So I'll put on my scientist hat now, and I will just quickly speak about the guidelines for mercury monitoring for the effectiveness evaluation and the reasoning behind the document. So what was the aim behind the monitoring guidance document? So if we look at the aim and process of the monitoring guidance, I can basically sum up in these 3 points, is that the guidance is basically there to explain the role of monitoring in the effectiveness evaluation and set realistic expectations of what can be learned over time. Also, the guidance is there to provide guidance to parties and organizations that are currently conducting monitoring programs on what data and accompanying information would be useful for the effectiveness evaluation. And also, thirdly, the guidance is there to provide parties and organizations who wish to develop new monitoring programs. And we definitely hope that this will happen, as there is definitely a lack of data, especially in the Southern Hemisphere. So the guideline also provides inputs into how to develop new monitoring programs. So if you look at how everything was put together, so there was a roadmap developed by the COP, and the annotated outline was there. And this was then presented to 4 consultants, and we further developed it. And from July 2020 until the whole of last year, there was a lot of online meetings, input from parties and from experts. Eventually, when we have the draft monitoring guidance at the state where it is currently. Struggling to get to the next slide. Let's check. Okay. So in terms of the process, the executive summary in chapter 1 and 2 was done by UNEP. Emanuela and Isaku was very instrumental in that. Chapter 3, which focused on the atmosphere, was done by myself. And then there were 3 other chapters that focused on biota, human biomonitoring, and cross-media data analysis. And these were done by Dave Evers, Neil Basu, and Colin Thackeray. And then there's also a supplementary section, part 1, which focused on the monitoring program and SOPs. And then also part B, which focused on QA and QC procedures. The way that the guidance is structured is that in chapter 2, we proposed a tiered approach. And basically the idea behind the tier approach was to cater for all the parties and all the different needs, because we have parties that have no monitoring activities or experience, and then you have parties that has been doing mercury monitoring for some time now. So the tier approach is presented where the tier 1 will focus on limited set of parameters where the methods are cost effective, practical, and feasible. So this is for parties that will be starting out that has got no experience or no monitoring program at all. Then tier 2 is a bit more advanced, focus on the basis for assessing source and attribution at the local, national, and global scale. This is also where research comes in. So this is where a party might have a network of stations, and that has been running for some time now. And then tier 3, which is the higher tier, is basic for understanding key processes that link the environmental concentration and the exposures together. That the slide's not changing. It's okay, yeah. So chapter 3, which I was responsible for, starts with the following, and it asks, why atmospheric mercury monitoring? And as Isaku has alluded earlier, that Article 1 of the convention speaks to protecting of human health and the environment. That's one of the key aspects. And also at previous COP meetings, there was an ad hoc expert group that was appointed by the COP to look into the effectiveness evaluation. And out of that report from that ad hoc expert group, they concluded that that A is a suitable matrix definitely to help evaluate the convention effectiveness. So that's why A was one of the matrices that was chosen for the monitoring guidance. Also, as we know, is that mercury is a natural occurring element which is emitted to the atmosphere from a variety of sources, and that is basically the main pathway into the rest of the environment. And for today, we will then basically focus on the two species which I've highlighted here today. So we know that there's basically three mercury species or fraction or forms that is commonly found and measured in the atmosphere. This is your gaseous elemental mercury, which there's a lot of work done, a lot of work published on this, and then the gaseous oxide mercury, and then particle bound mercury. And if you measure the two of them together, then you basically get the reactive mercury. What I should highlight also is that for GEM or for total gaseous mercury measurement, these methods are well established and good comparability has been achieved already. There's hundreds and hundreds of papers out there already. But in terms of the speciation of mercury, at this stage, there has been some comparison studies, which the results was satisfactory, but there's definitely room for improvement as there is still a lot of uncertainty associated with how things are currently done, especially with the commercial available instrument there. So this will then basically be the focus of our talk today on the reactive gaseous mercury and the challenges and what is happening in the new developments. Next slide. Okay, so why are we interested in measuring reactive mercury for the effectiveness evaluation? And basically is that atmospheric reactive mercury is meaningful and useful as it reveals the behaviors of regional atmospheric mercury cycles and identify the contribution of regional emissions. It's also important as it provides valuable information, especially if we are looking at modeling and help evaluate this model. It's also important to understand the short-term oxidation processes regarding the removing of mercury from the atmosphere. And then one key thing, and this will definitely also come out later in the talk, is that monitoring of reactive mercury for the effectiveness evaluation will only be beneficial if there's a agreed upon the reliable and accurate method for this. And this is where new research comes in, which also speaks to Article 19 of the Minamata Convention. Slides is changing very slowly. Sorry for that. Okay, so the reason why the tiered approach was also very important is that if we look at currently what the numbers are for the Minamata Convention, we have about 135 parties that have ratified the convention, and fewer than 20% of these parties have an air monitoring program that is currently active, and that is very important, that is currently active. So the guidance looks at parties with no monitoring, parties that can do one of the methods, maybe wet deposition that is commonly used in the APMMN network. And then there are parties that use various forms of techniques. And then there are also parties that have a network of stations located throughout their countries. So the tiered approach is basically the best way to meet all the parties' needs, that no party is left behind in making mercury history, which is the slogan for the Minamata Convention. When we look at the tiered approach, and this is also part of the supplementary data in the guidance, is that if we look at either GEM measurements, wet deposition, or total gaseous mercury as a tier 1 measurement, The idea behind this is that it's supposed to be cost effective, practical, feasible, and sustainable. And also it must be easy, as most of the parties that will start out with a tier 1 monitoring will have no experience or very limited experience with it. And the ideal way to start with this would either be with passives, which is very easy, wet deposition, or with manual method to do this tier 1. And the advantage of this is that from the analysis, if you look at on the right-hand side of the column, it's supposed to be highlighted, but say these are all the outputs you can get from something as simple, I would say, as a tier 1 approach. If you look more at your tier 2, the methods become more advanced, also more cost involved with that, but then the output is that you will definitely get more in terms of your estimate, in terms of your air, ocean, air, terrestrial mercury exchange. But from a scientific point of view, these information is helpful, which we want to know. But if you look at from a quality perspective, the output that we will get from tier 1 will be very sufficient. Still waiting for the final slide to come up. For some reason, let me just go out of presentation mode quickly, and then just put the final slide on. So tier 2 and tier 3 monitoring provides the opportunity for reactive mercury, also for new research. As Isaac has also alluded in the beginning, we have to investigate that how can this help the convention on monitoring to maintain harmonized, but more important, comparable information on mercury levels in the environment. Reactive mercury research also speaks to Article 19 of the convention. So these new and current developments will be very helpful in that, and also supports the convention in that. And then my final point is that the following slides or the following talks will definitely highlight the current and new research approach for improving our understanding of reactive mercury measurements. Thank you, Isako.
Thank you, Linville, and thank you for reminding us about the various use of monitoring data, not only for the effectiveness evaluation, but for as a scientific basis, which is not only of course Article 19, but the basis of other specific measures on emissions and HGM and so on and so forth. So thank you for that. And then I would like to turn to Iris, who is going to make a brief presentation on the elemental mercury measurement. Iris, over to you.
Yes, thank you. In my case, good afternoon, everybody. My name is Iris de Krom. I'm from VSL, which is the National Metrology Institute in the Netherlands. And today I would like to talk about metrology and why this is so important for the Minamata Convention, especially the effectiveness evaluation, and also about the comparability of measurements results for gaseous elemental mercury. So metrology is the science of measurements. Measurements are important in many aspects of daily life. So when you go shopping, you want to pay a fair price for a kilogram of apples and a fair price for a liter of gasoline. And in order to make sure this happens, balances need to be calibrated, or the pump needs to be calibrated for volume. Also in sports, measurements are very important. When you think of the world records that are very close together, you need very exact measurements to determine the differences between first and second place. But also in healthcare, it's very important that we can make exact measurements and determine diseases or diagnose diseases. In science, also measurement is very important for innovation such as green fuels, radiotherapy, nanotechnology. and there metrology helps. But of course, also for mercury measurement results, metrology is very important. But what is metrology? Let's look at a few definitions. So metrology is the measurement of science, as I already said, and since 1960, it's the basis for measurements has been defined by the Essi units, or the otherwise known as the metric system, so the international units or the international standards. And in a measurement, there is always a comparison between an unknown quantity and a quantity with a known, which is known, which can be a standard or a reference material. And this quantity also has a known uncertainty, which is very important in metrology. And in order to be able to compare together measurements that are conducted in different places at different times, the measurements must be traceable. So therefore, metrologically traceable is very important because it refers to an unbroken chain of comparisons related to a measurement result. And how is this arranged internationally? So the international standards like the kilogram, the second, the meter, they are maintained by the BAPM in Paris. And each country has a national metrology institute, and the national metrology institutes maintain their national standards, which are directly traceable to the international standards. And from these standards, reference materials or working standards are prepared or are developed, which can be used by calibration laboratories, industry and testing laboratories to ensure that also their measurements are directly traceable to the international standards. So the traceability to the international standard is regulated via the National Metrology Institutes. And as I said, these National Metrology Institutes have the public task to maintain and develop the national measurement standards. Therefore, NMIs create their own realizations of these standards, and they compare these standards with each other to ensure their comparability. And we do this in key comparisons. And as I said, national standards are then used to obtain working standards or calibration standards, reference materials, which can be used in the field by industry or by monitoring programs to make sure that they can also obtain metrologically traceable results. And also for mercury measurement results, traceability is important. Mercury is measured all over the world at different places, different times. And how can you assure that all these measurements are comparable with each other? That's by using international standards. And this can help to evaluate the effectiveness evaluation for the Minamata Convention by just using these international standards. So in Europe, we have been working in the past decade on the development of measurement methods and reference material for gaseous elemental mercury. And we have been doing that in various European projects, so with other European National Metrology Institutes and partners from industry. We have been working on this under Euramet, which is the European Association for National Metrology Institutes. And we started in 2010 with a project called Part Emission. And in this project, reference materials and methods were developed for soot particles, platinum group elements, and for mercury. So mercury was only a small part of this project, but here the first developments were done to obtain a primary standard for gaseous elemental mercury. In 2013, a second project started, the METRA project. And in this project, traceable calibration methods for mercury in all environmental media were developed. But in this project, we went on with the development of the primary gaseous elemental mercury standard, and we performed the first validations to show that this method is working. So after that, the MERC-Ox project started. As you all know, oxidized mercury is very reactive, and also for this species, it's very important to have traceable calibration methods. In the MERC-Ox project, we developed a method to ensure traceability for oxidized mercury species starting from the gaseous elemental mercury traceability that we have established in the previous two projects. I won't be talking anymore about oxidized mercury, but in the presentation after me, the presenters will tell you much more about this. I will talk a bit more about gaseous elemental mercury. So the last project we are currently working on is the Essi mercury project. And in this project, we are developing and validating protocols for the calibration of the output of elemental and oxidized mercury gas generators to ensure that the methods that we developed in previous projects will be written down and can be used by industry and monitoring programs to ensure that the calibration chain from the National Metrology Institutes will be used in the field by industry and by monitoring programs. So what have we exactly developed? A primary mercury gas standard. So this is a standard which is directly traceable to the international standards. Therefore, we call it a primary standard, and it has a known uncertainty. And with our standard, we can generate gaseous elemental mercury concentrations in air. And at VSL, this method is based on the diffusion method. Next to the method that we have developed at VSL, NIST, which is the National Metrology Institute in the USA, also has a method for traceable calibration of mercury in air. And this method is based on spectroscopy. If you're interested in more details about these type of measurements, you can read the articles that I've attached in this slide, or you can always ask me for more information. So as I said, once we have developed such a standard, it is very important that we compare this standard with other institutes to ensure that we are comparable. So we organize comparisons. One of the comparisons we organized was between the VSL generator and the NIST standard reference material. So the GSI Institute, where Milena Hofvat works, they use this NIST standard reference material to calibrate their systems. And we compared this with the VSL gas generator. And as you can see in this graph, they are quite comparable. So there's a little offset of plus 1.3%, but that's well within the uncertainties of 3 and 2% for these measurements. Another comparison that we performed was against the Dumaré equation. This is a method that is used a lot in the field. It is not a primary method. It is not traceable to the international standards. And as you can see, there is quite a deviation between VSL and also NIST and the Dumaré equation. So when you use the Dumaré equation to calibrate your systems, you will have a bias in your measurements. We have found this bias during our measurements, but this bias has already been known and also published in articles before. And we see the same negative bias here. So these results are very important for us to show our comparability with other measurements for mercury. So we have developed this primary mercury gas generator. And with this, we can ensure that measurements of gaseous elemental mercury in emission sources and in the atmosphere are traceable. And we've shown that our standard is comparable with the NIST reference material and that it has a bias compared to the Dumaré equation, which is comparable with literature reviews. So what can we do with this primary standard? Based on this, we can provide calibration services to calibrate mercury analyzers or to calibrate the output of mercury gas generators to ensure that in the field, people can also use this traceability or this metrology. So what are we currently doing for the future is, as I already said, in this Essi Mercury project, we are developing and validating Essi traceable protocols to determine the output of mercury gas generators which are used in the field. And once we have validated these protocols, they can be converted into written standards through international standardization organizations to make sure that industry and monitoring programs can use these protocols. And this will ensure an unbroken chain of measurement results from the primary standards at national metrology institutes directly to industry and to monitoring programs to ensure that mercury measurement results are reliable and comparable all over the world. So thank you for your attention. And if you have any questions, I'm happy to answer them at the end of this session.
Thank you. Thank you, Rhys. So since we are a bit behind time, I think we move on to the next presentation, which is the a series of talks of researchers, scientists of the both sides of the Atlantic. So now I would like to ask May to start the presentation, and she will switch to other speakers depending on the topics that are presented. So May, over to you.
Thank you, Isaku. Good morning. What we are going to talk about in the next presentation is just demonstration of oxidized mercury measurements and calibration. And this presentation was put together by myself, Seth Lyman from Utah State, Sarah Dunham-Cheatham from University of Nevada, Reno, and Milena Horvat from the Joseph Stefan Institute in Slovenia. And we really appreciate the opportunity to be able to present work that we have ongoing. Next slide, Sarah. So I'd like to just start this out by pointing out that the scientific process is learning, gaining knowledge over time, and our progress is made as our knowledge increases and our methods improve. And just think about how long it took for scientists to realize that the atom was made up of protons, neutrons, and electrons. So it's a process, and this is what's going on with our ability to be able to measure reactive mercury. So next slide, Sarah. So oxidized mercury. So this is particulate bound and gaseous oxidized mercury that Linwell introduced. And why is it important to measure? It's emitted from point sources at high concentrations. It's also present in the air that we breathe, or what we call ambient air. And so point sources emit it. And then in the atmosphere, we have reactions with elemental mercury that create oxidized mercury. It also can be emitted from natural sources. And here we're going to just focus on ambient atmospheric measurements, not emission measurements. Next slide, Sarah. So as you can see from this little schematic, atmospheric mercury chemistry is very complex, and we are constantly learning new things about it. Oxidized mercury is very difficult to measure. It's sticky. It sticks onto surfaces. It's reactive. It can be reduced to elemental mercury depending on atmospheric chemistry. And we're also measuring really low concentrations. But as Linwell pointed out, oxidized mercury is what gets scrubbed out in rain. So it's more readily deposited to ecosystems. And then in ecosystems, the mercury 2+ form can then be methylated more readily than gaseous elemental mercury. So it's important to focus on this form. Methods to measure have evolved over time. We first started with manular denuders, so just a single denuders that we would take out and collect oxidized mercury or gaseous oxidized mercury, and then filters were being used for particulate bound mercury. And then Techran Instruments, in collaboration with others, developed an automated system for operationally defined gaseous oxidized mercury and particulate bound mercury. And this became the instrument that scientists were using. Next slide, Sarah, please. And so basically there's different ways of collecting oxidized mercury, and the Techran uses a KCl denuder, which is the top figure. And the issue with the denuder is that the reactive mercury, oxidized mercury, adheres to the denuder surface, and then depending on the atmospheric chemistry, this oxidized mercury that's collected on the denuder can be reduced to elemental mercury. And so this is something that we've realized. The bottom diagram shows collection of oxidized mercury on cation exchange membranes. And this is currently a method that we are working with because it effectively collects gaseous oxidized mercury and doesn't release it due to atmospheric reactions. Next slide, Sarah, please. So the Techran system, basically, you can see on the right panel, you have the air passes through the denuder and then a particulate filter and is collecting oxidized mercury over 2-hour roughly intervals. Meanwhile, the Techran 2537 measures gaseous elemental mercury, and then the denuder gets heated up sequentially and the particle unit gets heated up, and it's converted into gaseous elemental mercury because all our actual measurements are gaseous elemental mercury. And so this instrument is being used in networks worldwide. However, there's high uncertainty associated with these measurements, and it's been demonstrated that the denuder measurements are biased low by 2 to 13 times. And there's no ambient air field calibration for GOM or PBM. So therefore, this instrument that we've been using is not calibrated, which significantly affects our certainty whether we're making accurate measurements. Next slide, please, Sarah. So because of this, it's become clear that the Techran measurements are impacted by the chemistry of the atmosphere, and we need new accurate measurements for GOM and PBM. And actually, that's something that my group and also Melena's group have been working on for quite a while. And we're just going to take you through showing you some of the different methods that we've developed. Next slide. Oh, and we need calibration that's traceable to an international standard. And so that's the other thing that groups have been working on, is achieving a calibration standard. And this is not easy to do because reactive mercury is sticky. So you need to somehow get reactive mercury into your analyzer so that you can use the calibration to check whether your measurements are accurate. And we need a SI traceable or a globally agreed upon calibration method. And just to kind of reiterate, we need global comparability, as Iris mentioned, traceability to a standard that can then be used globally to make sure that we're all using the same calibration and we're all making accurate measurements.
So to work toward that objective of having measurements that are all alternatives to the Techran speciation system, our team, as well as others around the world, have been working to develop alternative methods. We're going to present two kind of categories in our talk here today. The first one is the Reactive Mercury Active System, or what we call the RMAS. This is a simple membrane-based measurement system capable of measuring reactive mercury, gaseous oxidized mercury, and particulate bound mercury. And this is developed at the University of Nevada, Reno by May Gustin's team. The second type of system that we'll talk about today is what we call a dual channel system. And this is a more automated system, often coupled with a Techran or a Lumax analyzer. and they're capable of measuring reactive mercury as well as gaseous oxidized mercury. We'll talk about two particular dual channel systems today, one that's been developed by Seth Lyman and May Gustin, and the other that was developed by the MERCOX project, and Melina will present on that. However, it is worth noting that there are other teams, including NOAA, that are working on alternative dual channel systems to the ones that we were presenting here. So the first system we'll talk about is the Reactive Mercury Active System, or the RMAS. So we have a little schematic here on the right of what the system looks like. It's just a 6-port active system, meaning that it has vacuum pumps actively pulling ambient air through the membranes. The collection surfaces here are ion exchange membranes that capture either reactive mercury or gaseous oxidized mercury plus particulate bound mercury, depending on the configuration of the membranes within each of the filter packs labeled 1 through 6 in this diagram. The main benefits of this particular system is that it is low cost relative to the other systems that are currently being developed. It's fairly easy to use, it's rugged, it can be field deployed, it withstand a lot of different types of climates. However, it does have a 1 to 2 week resolution depending on the concentrations of mercury in the ambient air. And you'll note here in a couple of slides that the other systems have 10-minute resolution. So in this case, we have a little bit longer temporal resolution. However, depending on the research question at hand, we are capable, or the system is capable of measuring reactive mercury concentrations or chemistry, or separating particulate bound mercury and gaseous oxidized mercury concentrations or chemistry. And depending on the research question, we can mix and match these configurations to ensure that we have plenty of sample replicates to address and assess these different types of mercury measurements. Now, the Reactive Mercury Active System has been deployed across the globe. Within the contiguous United States, we have deployed the system at 8 different sites, all with different climates to assess the robustness of the measurements in different air chemistries and temperature and metrology type applications. We've also deployed the system at Mauna Loa's Observatory on Hawaii, Svalbard in New Allison, and a couple of locations in Australia, and the system is currently being deployed on Amsterdam Island. Once the membranes are sampled from the system, they can either be analyzed for total mercury concentrations. This is done through digestion following standard method EPA 1631. This is traceable to NIST standards as well. And then the resulting digestate is analyzed by cold vapor atomic fluorescence spectroscopy on a Techran 2600. Alternatively, we can assess the mercury chemistry with this type of system, and this is done through thermal desorption. So basically the sample gets heated slowly, and depending on the gaseous oxidized mercury or particulate bound mercury or reactive mercury compound that is on the sample, the compound gets heated off at a characteristic temperature, and then we can analyze the total mercury downstream and determine what the chemistry is or was on that sample based on the colored bands through which that sample comes off. And with that, I will turn it over to Seth to talk about dual channel systems.
So, but dual channel systems have kind of emerged as an alternative to the Techran speciation system that May talked about that hasn't been performing as well as hoped. And they use the same basic technology as the RMAS system Sarah talked about. At least most of them do, I should say. That's not a requirement, but they use the cation exchange membranes, and so they sample air in an inlet and then split into 2 air streams that are analyzed in a different way to kind of indirectly get at the oxidized mercury concentration. Sarah mentioned they're being developed by several teams around the world. Next slide, please. So this is a really simplified diagram of the dual channel system that I've been working on. As you can see, the 2 channels are, the first one has a pyrolyzer at the top that is hot enough that it thermally decomposes oxidized mercury compounds to elemental mercury. So that's a measure of total mercury in the atmosphere. And then the other channel that you see on the bottom is essentially the same as the RMAS system, at least some of the channels of the RMAS system. It has cation exchange membranes to collect oxidized mercury compounds, but those membranes allow elemental mercury to pass through. So you have one channel that's total mercury and one that's elemental mercury. Next slide. So, and then the next slide after that, please. So channel A measures total, channel B measures elemental, and you take the difference of those to get oxidized mercury. And we can do this, next slide, please, in about a 10-minute time resolution. Oh, maybe I went too far, but that's okay. About 10-minute time resolution. And with the detection limit, that's worse than the RMS because we're doing it at a high time resolution, but still good enough, as I'll show in a slide later, to detect short-term changes in the mercury chemistry of the atmosphere. Okay, next slide now, please. So along with those measurements, then our group, as well as others, have been developing calibrators for oxidized mercury, as we talked about a little bit. The goal of all of these is to have something traceable, as we've talked a lot about, comparable, stable over time, but also it needs to be field deployable because we need to measure mercury in very different environments around the world. And ideally, it would also be economical and user-friendly. And we hope to soon do intercomparisons of different calibrators being developed. Next slide, please. To our knowledge, at least, the types of calibrators being developed are involve, or at least the basic technology is permeation tubes. That's what we're working on. Also diffusion tubes, similar to what Iris de Crom talked about. Also liquid standards that contain oxidized mercury that are aspirated or evaporated into an airstream, and then kind of on the fly generation of oxidized mercury from elemental mercury using a plasma technique that Milena Horvat's going to talk about a little later. Yes, let's go on to the next slide, please. So the calibration system that I've been working on uses permeation tubes. You can see a photograph of one of them here on the left side. Basically, all it is you take a mercury compound, what you're seeing here is mercury bromide, put it in a tube, plug the ends, and then if you keep it at a constant temperature, the rate at which the mercury bromide evaporates or diffuses through the tube is constant for that given temperature. So you can pass air over that permeation tube and have a constant concentration of oxidized mercury coming out. On the right side, you can see the analysis of the effluent from that permeation tube in a gas chromatograph and mass spectrometer. And without taking too much time, it shows with the mass spectrometer that what we're seeing coming out of these perm tubes is in fact gas phase mercury bromide. Next slide, please. So where I am right now is at Storm Peak at in the Rocky Mountains, where we're testing our dual channel system and our calibrator. And you can see both these systems on the roof above where I am now. So the calibrator feeds oxidized mercury concentrations or oxidized mercury into the dual channel analyzer. And on the right side is kind of a simplified image of some of our calibration results, actually from a previous study elsewhere in Colorado. And the dual channel system was able to recover oxidized mercury compounds with a decent amount of uncertainty, but within the range of what was expected, whereas the KCl denudor-based system wasn't able to do that. So the calibrator, there's the figure on the right kind of glosses over a lot of uncertainty left, a lot of development still needed, but it definitely all signs are pointing in the right direction that the dual channel system and the RMS system are able to measure oxidized mercury as far as we know now quantitatively, and the calibrator is moving towards being able to routinely do that calibration. Next slide, please.
Okay, this is Milena speaking now. So what we have heard is about permeation, calibration source. There is also diffusion that will all be like in the gaseous phase, but there is also liquid evaporative gaseous oxidized mercury calibrator and newly developed cold plasma. These last two I'm going to shortly address because all of this is quite well addressed in the publications that you are going to see. So liquid evaporative gaseous oxidized mercury calibrator is basically taking mercury 2+ in reagent solution, sucks it up into the evaporator, and then this goes directly into the mercury measurement unit. In this case, this is mercury continuous emission monitoring, which is very much used in when we measure mercury in emission sources. So what is next, please? What is good about this here, that when we talk about traceability, which we have seen now to be a fundamental thing for comparability, this could be traceable to NIST 3133 or NIST 3177. One is both, of course, are Essi traceable certified reference materials produced by NIST. And then next. Now, this process goes really pretty well. However, when this mercury vapor comes out of the evaporator, there could be mercury zero impurities. So how do we manage this if we want to, let's say, use this kind of an approach for oxidized mercury measurements? Next slide, please. So within the MERCOX project, Opto7 and VTT from Finland developed so-called simple dual system by which you measure total mercury, which, this is like oxidized mercury coming into the system. Then you measure total mercury linked to one Lumex unit, which measures it like this. But then at the same time, we also measure elemental mercury in the system because, atomic absorption system will only measure when mercury is in elemental form, and when in oxidized form, this will not be detected. It has to be transferred into elemental mercury. So if you measure Ag0 impurity in this case and total mercury, then from the difference, you will have gaseous oxidized mercury. It's a fairly system that is fairly simple. It has been used a lot within the MERCOX project, and it's basically developed to the stage that can be commercialized. Next stage, please. Next one. Now, this has been primarily intended, initially it was intended to be used for higher concentrations like in emission sources, but then we tried to see how it operates at lower concentrations. And at lower concentration situations really change, because as you can see here with this this color here, with the lower concentrations, we see that we lose a lot of this mercury. And in this case, basically, because it sticks to all the surfaces, is a terrible thing, the oxidized mercury, when it comes to low concentrations. And everybody understands it pretty well. And so what we see that with liquid evaporative calibrator, we are very difficult to get close to state any traceability to Essi standard indeed. And that was in a way disappointing, but again, that is also the point of departure for something new to develop. Next slide. So we thought if we have our Hg0 traceable, and that is possible as Aris presented at the beginning. So we said, why don't we use Hg0 either produced from Essi traceable liquid standards, where we transfer Ag2 to Ag0 and use that as an Ag0 source, or use an Ag0 source that is Essi traceable. And then if we mix this with either air, chlorine, and bromine gas, and we submit this to the low temperature plasma in helium, we have achieved basically 100% oxidation of elemental mercury that is traceable. And then we were thinking, okay, this principle works pretty well, and it's very cheap, very simple, because you just have to apply current, high voltage, and that is all. And that is possible to load the neuters, if you like, sorbent traps or membrane traps. This is now being developed. It's more complicated, but in the end, it will work. Now, what is very important is that we don't have any breakthrough of elemental mercury. So we are, in fact, coming close to, let's say that Ag, gaseous oxidized mercury, can be traceable to NIST certified reference materials. And next one, please. This is just another look how one can also produce plasma in a denuder. In the denuder, this is simple. Next, please. So how does this really work? The principle of operation, you have to have helium gas. We are talking here about non-thermal plasma, where most of the energy used is to produce energetic electrons, while the thermal plasma in energy is also converted into heat. So we don't have heat here. We have atmospheric pressure and low temperature plasma. Next, please. And so when you submit to this flow also either air, so oxygen, chlorine or bromine, together with traceable quantity of Ag0, you are producing mercury 2+. Next, please. And then, next, please. And then what you get basically in there is different mercury compounds, which is the same as used in the research in the United States. You can very clearly see difference between mercury oxide, chloride, bromine, and other species. This is just to illustrate in a simple manner. The difference here is that we use temperature programmed desorption connected to the quadrupole mass spectrometer, which in fact is so sensitive that we can see below picogram per picogram levels once we produce these compounds. Next, please. Yes, this is just here for qualitative validation only. If we want to measure total mercury, then we have to transfer all to Ag0 and then measure by atomic fluorescence. Here is just to demonstrate that even at these low concentrations, we can see there are different mercury species there. So the point here is that this offers really to mix different gases and produce what we would like to have, because we know that in the atmosphere we not only have mercury. When we talk about gaseous oxidized mercury, we sometimes don't know what these compounds really are, and so we can also calibrate for this different mercury species. Next one, please.
So this slide just shows the output over a few days of our dual channel system at Storm Peak Laboratory in the Colorado Rocky Mountains. So it's a time series on the x-axis from June 7th to June 11th of the last year. You can see elemental mercury is the blue trace and oxidized mercury is the red trace. This site is high enough that it often gets air from above the boundary layer of the atmosphere, so in the free troposphere. The free troposphere tends to be rich in oxidized mercury. So the only point we're trying to make here is that we can see rapid changes. As you see in the beginning of this time series, oxidized mercury is high, elemental mercury is relatively low, and then on the 10th of June, there's a rapid change as we move into sampling boundary layer air. So we're just showing this system is working, giving us reproducible or reliable results. Next slide, please. Oh, and I forgot to mention in the previous slide, you don't need to go back to it, but at Storm Peak, we're also doing an intercomparison with the RMAS system. We did a larger intercomparison in 2019, or starting in November 2019 through November 2020 at the University of Nevada, Reno campus, and that's the image you see here. There was a Techran speciation system. USU and UNR both had a dual channel system, and then the RMAS system was deployed in several configurations. And then if you click, so we can show the graph. There's a time series graph here over the period of the deployment, and you can see the orange and the blue are the RMAS and the dual channel. They agreed quite well over the study period, but the Techran speciation system gave much lower values as expected because we know it has a low bias. Next slide.
Okay, so to conclude, we're making progress towards development of oxidized mercury measurements and calibration methods. Our new methods are demonstrating comparability and using the calibrator based on the permeation tube We're demonstrating that we're making accurate measurements by the RMAS and the dual channel system. And Seth has a paper on that, and we have a collaborative paper with Seth that is soon to be submitted. Next steps is to just continue development and testing of accuracy, precision, robustness, and comparability of newly developed measurement and traceable calibration methods. Traceability is key to comparability, so we need to harmonize these new methods. We need to come up with a calibration method that the global mercury community feels comfortable with. We need to do field and inter-laboratory comparisons to ensure that we have traceability, and therefore we can measure gaseous oxidized mercury in Nevada and measure gaseous oxidized mercury or oxidized mercury in South Africa. And we're going to know that we're getting data that's comparable because we have standards that we can use to validate this. So next slide. And then we need to really acknowledge the National Science Foundation because they have provided 4 grants that have supported our work over probably 12 years at this point. We also need to thank the students, both graduate and undergraduate, and Trevor O'Neill, who work in the Guston Lyman labs that are critical for keeping our work funding. And the Joseph Stephan Institute team acknowledges ARRS funding of the R Slovenia and European Union funding for the MERCOX and Essi Mercury projects, and also the GMOS train. So with that, I thank everybody for their attention, and we're happy to have discussion if people would like to ask questions.
So thank you very much. I think, Isako, now comes the stage for questions and discussions, right?
Yes. So thank you for your great presentations, and as I look at the chat box, there are 2 questions about the perturbations of the impact of natural and anthropogenic perturbations on Hg exposure risk, and also the thing about mitigation. I think this particular question is a bit beyond the particular scope of this webinar, but perhaps it may be related because as noted already noted, the oxidized mercury measurement is very much related to the fate of mercury after emission and deposition and so on and so forth. So perhaps this may be a good starting point for a panel discussion. So I just hand it over to Milena to convene the discussion.
Thank you. I have to say that I agree very much with you, Asako, that these questions are not directly linked to what we have discussed today, but indirectly, absolutely, they are very much in place because, in fact, understanding mercury chemistry, biogeochemistry, and fate in the environment, this will explain what happens from the source, no matter what the source is, and then finally what we are concerned most, and that is how mercury gets into the biosphere, and especially through the process of methylation, which is still a subject of a lot of research. And then when it comes to exposure of human population, then this is one further level of complexity. So there is no a very simple question, but I think we can all agree that measurements in this research have to be credible, comparable, traceable. Everybody has to be very responsible when producing data based on which some comparisons are done between different areas, in temporal scale. So no matter what we measure, is atmospheric mercury speciation, or we do speciation in aquatic environment or in biota, everywhere we have to be aware how important it is to demonstrate this comparability of the measurement results. So just addressing this first question, is somebody else who would like to add to this? If not, maybe just to say that, you know, what we have discussed today, how to measure oxidized mercury in emission sources, being in emission sources in the atmosphere, this will in fact direct how mercury from the atmosphere is going to reach the ground, terrestrial or aquatic, and then further on being methylated and going into fish, and from fish to human. So no matter it's natural or anthropogenic, it's all requires to be really very well understood, and measurements are needed for this. If there is no other thing, we can maybe go to the second question that is posed by Isato Sar. Now, this question is very much linked to the first question, I think, because it says that due to the complex nature of the biogeochemical cycle of mercury, predicting the net effect of altered loading of mercury, metal mercury, organic carbon, nutrient, sulfate, and other constituents on metal mercury accumulation in organisms remain a significant challenge. How this problem be solved? So anybody would like from the panel would like to address this question?
I can just make a comment that yes, the mercury biogeochemical cycle is very complicated, but I think we've made significant progress in understanding the interactions of mercury associated with carbon, nutrient, sulfate. This would be more in an aquatic ecosystem. I think that we've made significant progress in understanding it. And then but the fact is that mercury is transported and deposited from the atmosphere. And so reducing atmospheric emissions is extremely important, because that's how it's going to be input to ecosystems where it's going to be methylated primarily. And in order to do that, we really need to understand atmospheric mercury chemistry and concentrations. So,
yes, I think that was very much in place. That is one part of the big picture, and a lot of research is being done in this direction, and a lot of modeling efforts and improvements, refinements of these modeling tools, which are linking the emission to the uptake of mercury to fish. And I think this is very, very promising. I would say how this problem can be solved as an analytical chemist, I would say with a very, very responsible measurement infrastructure that will support all these different scientists to understand connections of all these different constituents, and that I think can, you know, lead us to an answer. We can get closer and closer. Okay, are there any other questions or comments?
Isaku has a question. Is there anything we can say from existing mercury measurements using the Techran? I would say that the elemental mercury measurements are good. But I would say that the oxidized mercury and particulate bound mercury measurements are not accurate, since the instrument had no calibration method. But we can use the data that we've developed over a long time using that instrument to at least try to say something about trends and impacts, but we should consider it to be not accurate. And as has been demonstrated, it's biased low. which I think is a significant finding, and that the fact that and the bias low depends on where you are in the atmospheric chemistry, because the atmospheric chemistry impacts the denuder that's in the instrument. Unfortunate. Yeah.
that I think, what I think comes out of all this is that we really have to work together as a global community to detect the issues and problems and try to solve them and try to find the way on which we agree, at least to the best of our knowledge and feasibility in what one can do. That is what we are doing at this seminar series here. In fact, inviting people to participate and to try to understand that these are still open issues. Even for elemental mercury, as Iris explained at the very beginning, this issue with Dumaré equation biased leads to lower results. I think this is also something that needs to be addressed. So we are not so straightforward, because 8% is something that one can manage if one understands where this difference comes from. Okay. There seems to be, there is more, yes. Since there is not my question, okay, this was then we have, are any of the new reactive mercury monitoring methods being developed in conjunction with Techran? Are they considered making changes to their instrument?
I can address that. No, we're not making, we're not doing anything with Techran. And I have no idea if they're considering making changes to their instrument. I would hope they would, but I think, as you can see, so we actually are, with this NSF grant we have right now, we're working on trying to develop alternate surfaces for collecting GOM or oxidized mercury. And one of our goals is to have something that could replace the KCl denuder. So we're actually working with a surface chemist who's with DOE, Department of Energy. And we actually are testing new surfaces in the laboratory. So hopefully through that research, we can come up with something. But I really think the dual channel system is it's a simple system, and it allows for getting at reactive mercury or gaseous oxidized mercury, depending on the configuration. And a lot of people have Techrans, and all you need to do is just change how you're loading mercury into the Techran. So it's a simpler system. It's not as complex as the Techran. So I think that the dual channel system is really a promising system for making close to real-time measurements.
Yeah, thank you. I think this is very promising. I know that there are other groups developing very specific, more specific trapping systems, so with the help of nanotechnologies also. I know that there are groups developing imprinted polymers that are going to be highly specific for different mercury species. And I think this is also very, very promising to see. And I think it's very important to try to maintain good collaboration with instrument producers, because finally all this knowledge and all of these developments will finally have to be somehow operationalized so that people can really use, because not every group that will do measurements will be as skilled to do them by their own. So it would be good if this new knowledge and development is being taken up by instrument producers and help people to get better results. I think that ICMGP is one forum like this. The seminar series is like this. So let's hope for the best and for good cooperation. I have extremely good experience with Lumix, though, in the MERCOX project, and now in SIAG. I mean, they are very open, and of course, within the limits of what Lumix can do for gaseous oxidized mercury, not so much at the atmospheric level, but at least in the emission sources, it's a lot of very good developments there. And standards are being there. But again, we will make progress as a global community. We have to agree on interlaboratory comparisons. We have to build these metrology services so that we know how to use these services and how to make progress in our measurements. If we are all going to just do it in our way, how do we do? While the others are doing this way, the others are doing in another way. So I think our responsibility as a global community, especially the research community, is to make an important impact to improve this situation. Okay, there is no more questions. Are there any questions that people would like to pose without a chat? Any comment?
So we don't see any chat, but if any of the audience have any other question, you can raise your hand. I think we can see it if there's any raised hand, but we don't see any hand. No.
That is fine. That is fine. I think it is a rather specific topic that will be visited by people probably when this is recorded and left on the UNEP's webpage. And I think we all are there to address any of the questions that you might have. I'd like to thank you all the attendees and all the presenters. And I think we can close the seminar. Isako, would you like to have the final word?
Thank you. Thank you, Milena, and thank you to all the presenters and audience. And perhaps I will say a few words to close, and Lynn may wish to say some words from the ICMGP perspective, and from myself, as the Minamata Convention Secretary, I was very impressed by this workshop, and also I think this was very good in for my understanding about the monitoring guidance for the effectiveness evaluation, where the gaseous elementary mercury and total gaseous mercury is listed for tier 1, and for the oxidized mercury it is tier 2 for more scientific research purpose, rather than just simply comparing the concentration from where to there. And also, although the emission monitoring was not the topic of this seminar, and also it may be rather from national perspective rather than the global perspective to look into the emission monitoring, but perhaps the Minamata Convention requires the secretary, encourages secretariat to cooperate in the scientific development. So I think there may be a opportunity for the Minamata Convention to support parties in that regard, to advance the methods for monitoring, including ambient and emission monitoring. So thank you very much, and I wish you the best workshop that you do at the ICMGP, and I hand over to Linville to close the session. Linville, over to you.
Thank you, Osaku. Yes, from my side as well, thanks to everybody for attending the session, all the speakers, and also the attendees from all over the world. I hope that, as Osaku was mentioned, there will definitely be a workshop as well as a special session that will focus on reactive mercury and these new advances that is being made. And as I've showed earlier, in case there's anybody that's either present now or that will be listening to the recording, there is still opportunity to submit an abstract the 15th of March. So we've been very gracious to all of you. So please go ahead and submit those extra abstracts. And I think we will probably also be back in April for another session on the Minamata Online. I'm not sure if the schedule has been finalized yet, Isaku. So I'm not sure what the next topic will be on, but I think we'll definitely have one by the end of April, if I'm not mistaken. But yes, from my side, thank you very much for attending this workshop. And we hope to see everybody again at the next Minamata Online session in April. So good afternoon, good night. Enjoy the rest of your day. That those that still need to work. Yeah. Bye-bye, everybody. Thank you.
Bye-bye. Thank you.
Bye-bye. Thank you.
Bye-bye. Bye-bye.